Alright, let's do a physics video this time. And this time we're going to be talking about linearizing the graph. And I think this is only something to do with physics 1, which is algebra based, nothing calculus, because the idea of it seems like very close to, just feels like a derivative would be a better option for that. But yeah, well, here we are. Anyways, I'm going to assume that none of you have taken calculus. If you haven't taken it yet, at least, and you're in this class nonetheless, we're going to talk about linearizing data. And the idea is very, very simple. So let's say I have data points. Let's stick to completely theoretical values right now. So let's write down A1, A2, A3, and by corresponding Y values, B1, B2, B3. And let's say the equation that relates these is a nonlinear equation. So what's your favorite equation? Natural log x? Okay, so let's say that y equals ln x, right? So this graph, if we actually graphed this, it would look like this, because this is ln x. So let's write this down, y equals ln x. And let's say this point over here is a1 comma b1, this point here is a2 comma b2, right? So on, so on, so on. Now, usually the idea behind linearizing data is never this simple, all right? You usually have an ln x, right? Never in physics, but this is just an example, right? Say you have like some random gibberish m1, gravitational constant, big R1 m over c squared, speed of light, I don't know why, but it's over here, ln x. This is going to be hard to manipulate because ln x is not a really friendly function. It's a very convoluted function, the base is irrational, it's has a restricted domain, all that stuff, So the idea is simple. If I want to get this, which is its stretch, right, on any graph, this is usually its stretch. If I want to manipulate this to find experimental values for capital G, say, right, this is just an example, keep in mind, this is nothing that would come up real, but let's just say we want to figure out capital G experimentally. We can't really do this with ln x, because it's, like I said, it was a really unfriendly function. So let's figure out if we can linearize this ln x. And the way we're going to do this is by using a substitution. And that's really what mathematically it is. And if the teacher did not say the word substitution, he really is doing a substitution. He just isn't using the word for it. But let's just use a new variable. Okay, in mathematics we call this dummy variable. But we can use any letter you like. We usually use u. I'm gonna let u equal to ln x. Right? Whenever we use a substitution, not only do we substitute everything that in terms of a new variable, we don't want three variables, right? The point of a substitution is to change variables completely. We want u's. We get rid of x's. We don't allow x's anymore. So since we're gonna use u, right, we're gonna do this. I'm gonna label this entire thing as capital C now. So I have to save writing space. U. So this is a linear graph now, but there's something that we need to change in order to make this a viable equation to manipulate, to take slope of. And that's because these x and y values have a ln x relationship, meaning that this will increase by 1, this will increase by ln of 1. You feel me? What we need to do is since we use a new dummy variable u, right, we need to make u variables that correspond to our y variables so we get a linear graph. Remember, our linear graph is y equals cu, right? We want to relate u with y. We got rid of x. That's the entire point of this substitution. So let's try and use some calculations to change our variables from x equals a1, a2, a3 to u equals whatever. So let's do that. So since we know that u equals ln x, right? ln x, what we're going to do is we're gonna plug in all your x equals values into ln x and get a new u value. So, for example, a1, we're gonna plug it into ln x, ln a1. Likewise, ln a2, ln a3. Now, when we plot points again, in fact, hopefully one of these markers is working. Let me just choose so I can so you don't get confused. Hopefully this pink marker is working. If we plot these points now, since we use a dummy substitution, it is not working. That is awkward. We plot our dummy substitution, it is working. Y equals some constant times u, or these whatever these constants are. We're gonna get a new linear graph in y and u terms. So let's do this. ln a1 could be any arbitrary value right here, like this, and we're gonna get something like this, right? Let's just label it ln a1 b1 ln a2 b2, right? From this point and this point. Hopefully you can see it. I'll be really awkward if you can't see it. I'll try and zoom in while I do it. But now that we have these, we can accurately see easily. We can actually measure our stretch, right? Without having to do any fancy derivatives, right? Systems, anything like that, right? So now we can find our slope in terms of these new variables that we got due to our substitution. So now we can get our slope to be ln of a2 minus ln of a1 all over b2 minus b1. This will automatically equal c, and say we're trying to make this equal to our c value, and remember c was this. So let me write this over here now. Right, now remember we were talking about finding the experimental value for g. So let's do that. C squared c, right? And then we can divide our m1, r1, m to get g. So that's the idea. Now we're basically finding stretch, right? By using a substitution to make a graph more linear, because linear functions are much more easy to identify a stretch because its stretch is a slope, and slope is really easy to identify. Unlike natural log of x, good luck trying to find stretch on that one. But yeah, that's the entire point of it. And I'll be uploading another physics video tomorrow.